Okay, here we go with the remainder of the second multiple choice. We're starting at number 23. When the equation below is balanced and all the coefficients are reduced to their lowest whole numbers, I'm going to rewrite this one right here because this is a good, tricky one to balance. Okay, so this is C10, H12, O4, S, and then we have oxygen, and then over here we have carbon dioxide, sulfur dioxide, this is an arrow, didn't make that big enough, and some water. And so my recommendation when you encounter something like this that looks somewhat like a combustion reaction is to do it alphabetically. So do the carbons, then the hydrogens, save the oxygens for last. You can notice that the sulfurs are already balanced, so leave that alone if you can. So for carbons, I'm going to need a 10 right here, okay, to balance that out. That gives me 10 carbons now, 10 carbons. Then do the hydrogens, and you'll notice I have 2 here, so I'm going to need a 6 here to get 12, okay. And then next, do the oxygens. And so I have way more oxygens on this side right now than I do over here, so let's take a look at how many I have. 10 times 2 is 20, plus 2 more here, plus 6 more right here gives me a total of 28 oxygens, okay? So right here I have 4, I'm not going to change that, but I could change this amount right here. And so what plus 4 equals 28? I believe that's 24, which would take a 12 right here, because 12 times 2 is 24, plus 4 more would give me 28, which would be letter C right here. So that's how I'd attack that one, alphabetically. C's, then H's, saves the O's for last. Okay, next then is 24, and this is a redox problem. It says, which of the following is true regarding the reaction? And it says represented above, but it's actually below. And so here, it's asking lots of questions about oxidation numbers, so I'm going to go and assign oxidation numbers to this first. So hydrogen is positive 1, which means the selenium right here has to be negative 2. OF2, so oxygen in this, fluorine's always negative 1. There's never a time when it's not, which means that oxygen in this case is going to be a really weird positive 1, totally wacko. Never see that except for when it's with fluorine. Over here, fluorine's negative 1, and then selenium right here would have to be positive 6 to balance that out. Fluorine here is negative 1, which means hydrogen is positive 1, and here oxygen is 0. So the oxidation number of oxygen is not changed. That's not true. Oxidation, because it goes from positive 1 to 0. Oxidation of hydrogen changes from negative 1 to positive 1. That's not true. Hydrogen is always positive 1 right here. Oxidation number of fluorine does not change because fluorine's always negative 1. In letter D, the oxidation of selenium changes from negative 2 to positive 6, and that is true. It went from negative 2 to positive 6 with some wacko thing happening to our oxygen right here. So letter D is our correct answer to that strange looking redox reaction. Number 25, a 0.1 liter sample of an aqueous solution contains 0.1 mole of the NaCl and 0.1 mole of CaCl. What is the minimum number of moles of AgNO3 that must be added to the solution to precipitate all the Cl minus ion is AgCl? And so you need to write the equation here for this one. And it's going to be a weird one. It's going to be our silver right here, okay? Silver from silver nitrate. Nitrate's going to do nothing in solution, so we're going to ignore it. And it's going to have to react with the chloride ion to make our AgCl right here, okay? Now it wants to know how much of this we're going to need. So what is the minimum number of moles of this that we're going to need? Now there's 2 sources of the chloride ion. There is 0.1 moles from NaCl, okay, so 0.1 moles of Cl from the NaCl, and there is 0.1 moles coming from the CaCl, CaCl2. But watch out, this has 2 chlorines in it for every one of these formulas or particles. And so technically, this is going to give us 0.2 moles of Cl minus. because there's a 2 right here, and it tells us it's 0.1 of CaCl2. And so our total moles of Cl minus are these two added together to start with. So I start with 0.3 moles of Cl minus. And it wants to know how many moles of this do I need to get rid of, or to take all of this and make it into AgCl. So if I were doing my stoichiometry steps, step number 1 would be to write this balanced chemical equation, and I wrote it as a net ionic. Step number 2, convert to moles, and I took my moles and I added them together to get my total number of moles of chloride ion in there. Step number 3 then would be to do a mole-to-mole ratio, and so I would do chloride ion to silver ion to find out how much silver I would actually need. And it's pretty obvious from this equation that it's just a 1-to-1 ratio. And so I would need 0.3 moles of silver ion to make that happen, which is letter C right here. The tricky part is just knowing that this CaCl2 gives you double the number of moles of the chloride ion right there. And then you can work the problem just like a regular stoichiometry problem. Okay, 28 is a recall question from chapter 2, and it says, which of the following is the correct interpretation of the results of Rutherford's experiment for which gold foil atoms were bombarded with alpha particles? So if you forgot that historic experiment that he did, here's a picture of it from the 13th edition of the textbook. And I'll zoom in on it just a little bit. And on here you can see that he had alpha particles, which are 2 protons and 2 neutrons. And he bombarded a gold foil piece with those particles. Most of them passed straight through, which is what he expected because the gold foil was so incredibly thin. But a few of the particles bounced off to the side or bounced straight back. And the reason that happened was because these particles would hit a small, dense, positively charged particle in the middle of the gold atoms. This showed that there was a dense positive nucleus in the middle of atoms. They didn't know that at that time, and so what this showed was that there was a dense positive part to these gold atoms, and therefore all atoms. And so the correct answer is letter E, is that there's a dense positive charge in an atom, and it's concentrated in a small region, and that small region is called the nucleus. Number 30, which pair of atoms represents nuclei that have the same number of neutrons? So let's take a look at number 30 right here. And they give you an isotopic notation right here. And let's look at letter D as an example. This is not the right answer. I'm just going to use it as an example, and then I'll go to the correct one. And this is nickel. I believe it says 59. And iron, Fe56. And remember, these numbers right here tell you the number of protons plus neutrons in the nucleus. And so it's called the mass number. And so for nickel, that would equal 59 total. And you could look on the periodic table and find out nickel normally has 28 protons. I mean, it has to have 28 protons. It's not nickel if it doesn't have 28 protons. And so the number of neutrons in this sample of nickel would be 59 minus 28. And so here it would have 31 neutrons. In iron, it would equal 56, and iron right here says it has 26 protons. That's what makes iron be iron. And so 56 minus 26 is equal to 30. And so this would have 30 neutrons in it. Obviously, those are not the same number of neutrons, so D is not the correct answer. Let's take a look at letter E. In letter E, they have nickel, and this time it says nickel 58, I believe. I'm just going to zoom in to make sure that I'm right on that. 58, I believe. Yes. And cobalt 57. Okay, let's zoom back out here. So nickel is 58, and that equals the protons plus the neutrons. And cobalt 57, and that equals the protons plus the neutrons. So if I look on the periodic table, nickel has 28 protons, and cobalt has 27 protons. and so I need to find the number of neutrons for each one of these. So 58 minus 28 means that this has 30 neutrons, and 57 minus 27 means that this has 30 neutrons. Oh, okay, so that's why letter E is the correct answer, because they both have the same number of neutrons. Number 31, which is the final concentration of the chloride ions when 250 milliliters of 0.2 molar cockle is mixed with 250 milliliters of 0.4 molar KCl solution? So this is a tricky one, number 31, because you're given two substances that both have chloride ion in them, and you're going to mix them. So first of all, I have 250 milliliters of the CaCl2 solution, and it happens to be 0.2 molar. And then I'm going to skip down a few lines right here, and I'm going to say I have 250 milliliters of a KCl solution, and this one's 0.4 molar. And it wants to know what's the final concentration of only the chloride ions. It wants to know just these. Tricky once again here, because you're going to get two chlorides for every one formula unit or particle of calcium chloride that dissolves. So the first thing I'm going to do is I'm going to take my molarity triangle, and I'm going to find the number of moles of chloride ion in the cockle. And then I'm going to do the same thing over here, or right below here. I'm going to find the number of moles of chloride ions in this guy right here. I'm going to add those two moles together, get my total number of moles of chloride ion, and then I will use the molarity triangle and divide it by my total number of liters, which is 250 plus 250, or 0.5 liters. All right, let's go through and do each part. So first of all, moles are equal to molarity times liters. My molarity is 0.2 molar times my liters, which is 0.25. So 0.2 times 0.25, 0.2 times 0.25 should be 0.05, yep. So 0.05 moles of CaCl2. Now I want to know just the chloride ions, so I'm going to have to multiply this by 2 for the chloride ions, because there's 2 for every one of these guys right here. So 2 times 0.5 gives me 0.1. So I have 0.1 moles of chloride ion from my cockle. Now my chloride ion from my KCl is going to be 1 to 1, so this one's easier. So my moles here is equal to my molarity, which is 0.4 molar, times my liters, which is 0.25, and I think I can do this one in my head, 0.4 times 0.25, but I'm going to put it in my calculator just to make sure. And I have 0.1 moles of KCl. And for every KCl, there's one Cl minus, and so I have 0.1 moles of Cl from this as well. So adding those two together, I have 0.2 moles of Cl minus divided by my 0.5 liters. 0.2 divided by 0.5 gives me 0.4. So my molarity of my chloride ion is 0.4 molar, which is letter D right here. Tricky problem. 32. What volume of water should be added, and I underlined that twice right there, to 0.4 liters of 6 molar H2SO4 solution to produce a solution that is 2 molar in H2SO4. So this is water being added to a solution, so immediately I go to my M1V1 equals M2V2 dilution equation. And so if I just rewrite this here and plug in my numbers, I'm starting with 0.4 liters, so that's my initial volume, okay? And my initial molarity is 6 molar. And my final molarity is 2 molar. And my final volume, remember this is my final volume, not the volume of water added, but my final volume of my solution. I have V2 right here, so divide by 2 right here. So let's just do the whole thing on the calculator. 6 times 0.4 equals divided by 2 equals, make sure I put multiply signs and divide signs, 1.2, so my final volume is 1.2 liters, okay, because I started with 0.4 liters. Now it asks how much water was added. Well, this is my total final volume. This is what I started with right here. So 1.2 minus 0.4 means that I added 0.8 liters of H2O to this. Because remember, this is my final volume, which includes the initial amount that I had as well. And so 0.8 liters is letter B right here. Careful of that one when they say amount of water added. Okay, and then 2 problems to go, I believe. Number 35. This problem right here you can't do yet unless you've had chapter 5, so skip that one. And then 35 said, which of the following represents acceptable laboratory practice? And letter C, adding a weighed quantity of solid acid to a titration flask wet with distilled water is totally an acceptable laboratory practice because the water is not going to change the number of moles of acid in a titration. Water doesn't affect the number of moles. It's just going to dilute it, but we're not interested in that. We're interested in the number of moles. And then number 36, the correct name for Ca3N2 is, so this is a single element, so it's going to be called nitride. It's going to end with an IDE ending. And this is going to be called calcium because it's an element in the periodic table in group 2 right here. And so calcium nitride would be letter B. That wraps up this portion of the multiple choice.